Hi folks, welcome back. So I am doing another video. It's during spring break, so you might notice I'm a little more disheveled, haven't shaved in a couple of days. It's more of my relaxed series of videos. Today we're going to talk about how to use the equilibrium constant. So we need to talk about something called a reaction quotient, and then we're going to talk about something called ice diagrams. So in the previous video, we went over what is an equilibrium, what's equilibrium constant, and this video we're going to start utilizing it and using it in actual chemistry. So just to review, equilibrium is a reaction that can go both ways. Most reactions are equilibriums. The perfect example though is kind of a phase change, right? Water can freeze and ice can melt. It's the same reaction just in opposite directions. So it's a reaction that can go both ways and can go both ways indefinitely. Some reactions don't. Combustion. You burn a piece of wood, that wood, you can never unburn it and get the piece of wood back. Okay, that is a one-way reaction. So there are some reactions that go one way, but most reactions actually are reversible. Phase changes, diluting something, redox reactions, we always talked about using the energy and then being able to plug it in and recharging the battery kind of thing. So all of those are reversible reactions, and most reactions in science are reversible. Some are very, very, very minorly reversible, and some are very reversible. So we're going to talk about a reaction quotient. So K value is the concentration of my products over my reactants. Q is found the same exact way. So Q is my reaction quotient. It's found the exact same way. It's product over reactant, right there. So I have my products. C and D are my products, over my reactants, raised to whatever the coefficient is. Okay. Um, and that's Q. It's found the same exact way as K. The only difference is Q is not taken at equilibrium. So at equilibrium, my products and my reactants are in equal concentrations, or not equal, the rates are in equal amounts. So my forward and reverse reaction, the rate is the same. So we don't see an appreciable change in concentrations, right? So I might have a ton of product and very little reactant, and I might still have atoms switching and changing from reactant to product and product to reactant, but they do it at the same rate, so that we don't really see it at all. Q is taken at any time other than equilibrium. And since it's not at equilibrium, we can't call it the equilibrium constant. So we call it the reaction quotient. It's the exact same way. It just gives us a snapshot of where the reaction is. Is the reaction not yet at equilibrium? Is it at equilibrium? Or has it even gone maybe a little bit beyond equilibrium and it needs to go back? Because there are certain things we can do to push a reaction past equilibrium. So that's kind of what Q is. Right? So if Q equals K, so if I find Q and it's the same as K, then the system's at equilibrium, right? It's at equilibrium, it's done. Now let's think of equilibrium as, let's say, a pendulum swinging, okay? So when it's at the very bottom, it's at equilibrium. Now before the pendulum gets to the bottom, it's before equilibrium, and if the pendulum swings past bottom, it's past equilibrium. So if Q is greater than K, that means there's more product than I should have, right? Because it's a ratio of product to reactant. So if my number is big, it means I have more product than I have reactant. So what happened was the pendulum swung past equilibrium. I have too much product and not enough reactant. And there's many, many ways we can do that. And we're going to talk about how to do that in a different video. But let's just say, so it's past equilibrium. What's going to happen is the system or the equation or the reactants and products needs to shift back to center or back to the left to center it back out over equilibrium. So I'm going to consume the products, because right now I have too many products because my ratio product to reactant is too big, and I need to consume the products and then form reactants until equilibrium is achieved. On the flip side, if Q is too small, that means I have too few product, which means it just hasn't gotten to equilibrium yet. All right, you took the reaction quotient, you took the concentration and found the reaction quotient at a time before equilibrium was achieved. And remember, some of these reactions are very long. Turning diamonds to graphites takes tens of thousands of years. So some of these reactions are very, very long. So if my Q is too small, it means that my pendulum hasn't gotten to equilibrium yet. So my system is going to shift to the right, consuming reactants and forming products. Okay, it's going to shift until I reach my equilibrium point. Okay, so Let's say we've got this sample problem. Now, so we talked about reaction quotients. This is ice diagram. So we're kind of shifting gears. We kind of brought up reaction quotients for a second. We'll come back to that a little bit more in class when we do stuff with it. But let's talk about something which sounds super cool, ice diagrams or ice tables. Not as cool as it sounds, but it's still kind of cool. All right, so let's say I have this reaction here. I've got water and carbon monoxide, and it's going to turn to hydrogen and carbon dioxide gas. Okay, and I have a K value. That's nice of them. They gave me a K value. It's 2. So that means I'm going to have twice as many product as I have reactant, right? Because K is product over reactant. So it's 2 over 1, 4 over 2, 6 over 3 kind of thing. Get it? So I'm going to have twice as many product as I have reactant. Oh, that's great. Okay. Now, let's say I start with 8 moles of water, or I'm sorry, 8 molecules of water, doesn't really matter, but 8 molecules of water and 6 molecules of carbon monoxide. How many molecules of H2O, CO2, blah, 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 are present in equilibrium? So how much of this stuff is at equilibrium? Now, normally, let's say you were in honors chemistry, you would assume that this was not in equilibrium, this was not a reversible reaction. You would assume that carbon monoxide at this point was my limiting reactant. I would consume all of my limiting reactant, and all I would have left at the end was product and a little bit of my excess O2, or H2O, sorry. Now, that's good, and that's fine, and that's great for a basic level of chemistry, but that's not really what happens here. It's a equilibrium. So it's saying that I'm going to have twice as much product as reactant, which is great. So I'm going to have a lot of product, but I'm also going to have some reactant. So not all of this carbon monoxide is going to be consumed. All right, so it's not like 6 molecules are going to transfer over like we would in a normal stoich. We would assume that all of that would be transferred over. That's not the case. That's not really accurate. Some of it's going to, most of it's probably going to go over, but there's going to be some left over at the end as well. Well, how do we do that? How do we calculate that? We do a couple of things. We're going to do what's called an ice table. And it's a much more accurate version of stoich. So stoichiometry assumes that all of my limiting reactants consumed. An ice table takes into account this 2/1 ratio, or my K value. So we first need to write the law of mass action, or write my K equation. And then we need to do an ice table, which I'll tell you about in a second. And then we need to put the two together. Okay, so first off, we're going to write our law of mass action. All right, now I know that it is product over reactant. All my coefficients are 1s, so that means that it's just everything's going to be the first power. So it's just going to be product over reactant. Right? And I know that K is 2, so 2 equals my products over my reactants. Nice and easy, no problem. Okay, so that was step 1. Step 2 is making an ice table. ICE is actually an acronym. All right, you might not have maybe realized, you probably realized that. So it stands for initials I, change, equilibrium. So initial, change, equilibrium. So here is my equation, and here's my ice table. Initial, change, equilibrium. Ice. Isn't that fun? All right, and notice each little thing has a box. That's cute. Okay, so initial. I'm going to plug in my initial concentrations. Well, H2O has 8, CO has 6, and then there are no products, 0 and 0. All right, now that was from the problem that we got. We remember we started with 8 waters and 6 carbon monoxides. How much of blah, 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 blah. So we have 8, 6, and since my reaction hasn't started, I'm going to have 0 and 0. Now C is change. So how much is going to change? Well, it turns out since the coefficients are all 1, I'm going to lose X amount of H2O, I'm going to lose X amount of CO2, and I'm going to gain X amount of H2 and X amount of CO2, okay? Now, if there was a coefficient in front of these numbers, there'd be a coefficient in front of these X's, right? If it was 2 H2O, well, then we would lose 2X, because we'd lose twice as much H2O as CO. But there's no coefficient, so these are all 1s. So we're going to lose X amount of this, X amount of this, but we're going to gain whatever X amount and X amount. Okay. Now in equilibrium, we just put these two cells together. So it's 8 minus X, 6 minus X, and X and X. So I'm going to start with sorry. I'm going to start with 8 H2Os, and I'm going to lose X amount of that at equilibrium. CO, I'm going to start with 6, and I'm going to lose X amount of that. And then H2O and CO2, I'm going to gain X amount, right? Or 0 plus X amount. Well, now I can take these and I can plug them into my K equation. all right, or my law of mass action. So I'm going to take these and I'm going to plug them into that law of mass action you wrote in step 1. So here's my equilibrium concentrations. I'm just going to plug these into my equilibrium expression or my law of mass action, and I'm going to solve for x. So it's product over reactant. So product is x over x, and reactant. H2O is 8 minus x, and CO is 6 minus x. Okay, so I just do my product over reactant. Now I know that equals 2. Well, at this point, great. You've got x's on one side, you've got a number on the other. You can do some algebra, and you can calculate what x equals, right? It's going to be x squared over this. You're going to FOIL this out. Remember, first, outside, inside, last. And you're going to get some sort of equation. Your x squareds are going to cancel out. And it's going to be a blast. You're going to love it. I'm sure you'll do fine with it. If you have any problems, you can let me know. There's some shortcuts we're going to learn. If you have a graphing calculator, we're going to do some shortcuts. You could graph this side. You could graph 2, and you could find the intersect. Because the intersect is when those two lines would be equal. But we'll get into all of that later. Okay, we'll get into all of that. The important thing is we plugged our x values in, or we plugged our values in for where they go, set equal to 2, and you solve. And if you actually did the algebra out, you would find out that x equals 4. Okay, so x equals 4. That's great. That didn't answer our question, though. Our question was, how much of everything is left at equilibrium? It didn't ask how much transfers. 4 molecules transfer, but that's not what it asked. So we substitute x4 in for x, right? And we get 4 waters. Okay, so we'd have 4 waters at equilibrium, 2 carbon monoxides, and 4 hydrogens and 4 carbon dioxides. Okay, so it's a little bit better than stoic. This process is better than stoic because it takes into account that there will be some reactant left. So that's why it's a little bit better. Stoic just assumes that all is reactant consumed. So, all right, so that's a basic ice table. Obviously, it was the first one we did. Obviously, I went very quickly. There's only one example. I'm trying to keep these videos short because you're on break as well. But we are going to talk about that much more in class. If you had no clue what's going on, I highly, highly recommend that you watch the video again because you are going to need to be able to do this and you are going to need to know this. There's also about 1 billion videos on YouTube talking about ice diagrams or ice tables. You can Google any of them. I'm sure some of them are even animated. There might even be a song about it. So, all right, I hope this cleared everything up. Good luck, and I will see you in class.